Please join me in welcoming Raquel.
Thank you. I know on the abstract that was sent out, it said static trust for network communication systems, and this says plug and play trust for embedded communication systems. And there's an interesting reason for this. We submitted this work is joint work that I did with Jack Harrison while he was a student in my trusted computing graduate class, which I teach next semester. And we called it plug and play trust because basically what we did was create this trusted image on a USB device, and so you could plug it into your system. Your system would make use of the trusted hardware and measure your whole system. So you had a read-only image, and we called it plug and play because you could plug and play and be in a trusted environment. So plug it in. But then we extended the work and wrote a longer paper, and there was someone was like, oh, we don't like the use of embedded because embedded talks about very device-specific types of systems, and when you think about routers and those types of things, they're not embedded in the traditional sense. So to appease the reviewers, we actually changed the name to static trust for network communication systems. So what we're looking at with regards to these systems are systems that don't change a lot. So they're kind of static. So those are the types of systems that integrity-based evaluations of those systems are useful approaches to evaluating a system to determine whether that system has been compromised or not. So that's why we're using this, and it's kind of a motivation. So we're going to talk about what is trust, you know, the problem, give you a background in trusted computing. I'm going to try to cram 4 weeks of lecture into I don't know, maybe 20 minutes, and talk about the plug and play or static trust architecture and future works and conclusions. So when you think about trust, trust is really a complex topic. And so we can break trust down into two types of trust. There's social trust, which is that I believe in something or believe in the safety of goodness of something because of its reputation, association, and its perceived benefits. And so when we're on the internet and we're just, browsing and we're interacting with websites, most oftentimes we're doing this and we're basing our trust of those sites on social trust. So if it's a large bank, or it's our bank or our credit card company, we see the emblem, we see the brand, and we trust because of its reputation or association. But there's also a behavioral trust, which says that I believe in the safety or goodness of something because it can prove that it's going to act in a trusted manner and that it meets some type of trusted criteria. And so when we look at trusted computing, basically trusted computing uses a combination of both social trust and behavioral trust. Social trust from the perspective that I have this piece of hardware that provides me with a separate execution environment that's separate from my host machine. So although it may be an adapter that's plugged into my machine, or it's on a chip that's on the motherboard, it provides a separate execution environment. So if the host is compromised, the chip itself and the software embedded within the chip is not compromised. Now we have a social trust in this chip because of the vendor, the developer, the brand of the people who are actually developing it. We're trusting that it's going to function as specified. So that's the social trust. Behavioral trust is that piece of trusted computing hardware actually allows us to measure our system. It provides us with some cryptographic functionality, that's embedded within the device that cannot be compromised, that when this device signs a particular piece of software, we trust that, that signature cannot be compromised because it's in the separate execution environment. So I can measure my system, sign it with this piece of hardware, and send that measurement off, and that's my proof that, this system meets some criteria. Now the criteria itself is determined a priori. So what I'm presenting to you today, I'm not telling you what is trusted or trustworthy. I'm just saying that if you have a specified criteria of trust, meaning that I have certain software and OS or a compiler that I'm using, or applications that have been certified to be trustworthy, whatever certification process you use, I can then measure that software running on your system, and then I can provide you proof that that's what's running. And there are some issues with, the whole architecture of trusted computing and what are you trusting, and we'll talk about a little bit of those and some vulnerabilities that we can't get around. But when we look at these types of systems and using trusted computing hardware, you know that there's no approach that's going to be an approach that's going to solve every issue. So I'm just going to give you that up front, because we can poke holes in that, but and there's always something, there's always a vulnerability. But this is something that we can do in addition to other security approaches to try to enhance the security of a system. Not completely secure, nothing will ever be, because there'll always be software and bugs, and we're not going to completely secure. So with behavioral trust, it's also known as certified trust or integrity-based trust. And trust doesn't mean trustworthy. So that goes back to, I can't tell you what, this work doesn't tell you what is trustworthy. It just says that if you've certified it and that's what you deem to be trustworthy, then we can actually measure that. And trusted doesn't mean flawless. So let's talk about the problem. Why are we looking at this problem as far as integrity? There's so much malware out there now, and machines are being compromised all the time. And when we have systems such as ATMs and routers and electronic voting machines, power grids, these are infrastructure-based systems. And so the compromise of these systems basically compromises our faith and trust, in this infrastructure that we rely on. So there's a big issue, with anyone that is familiar with the area. When the Trusted Platform module, which I'll talk about a little bit later, trusted computing was introduced, a lot of people were concerned that the device was going to be used to control our own personal machines, and limit what we could actually run on our machines. And vendors like Microsoft and developers were going to limit what other applications we could possibly run with their OS. If it wasn't Microsoft certified, we wouldn't be allowed to run it. So that was the issue early on. People were very concerned that, using some trusted hardware would take over the control of the machine. That is easier said than done. It is not an easy process to limit systems in that way using a TPM, because a lot of people have found ways to get around, doing that, breaking the system and loading whatever they wanted to load. There have been a couple of approaches, like I think early on, Macs were trying to use the TPM to force you to run specific code and stuff like that, but they abandoned those attempts to limit what you were running on your system. So it's not very useful if you're trying to limit systems that way. Where I think that it can be most useful is protecting infrastructure. These are systems that you don't expect to change much. You want them to work the way you want them to work. And if there is a change, that change in that system, more than likely it is a compromise. If it's not a change that has been certified and approved, it basically indicates that there has been a compromise. If you don't necessarily need to know what the compromise is, in these type of systems, you just want to know that a compromise is there and the machine actually needs some type of service, so you can rid the infrastructure of the compromise, because you don't want the compromise to propagate. You really want to limit that compromise. So when you think about, one particular example is that in 2009, institutions in Eastern Europe detected malware on their ATMs. And the malware was copied, the malware basically copied info on the magnetic strip and printed information on a receipt when a MasterCard was inserted. So basically someone introduced some malware to the ATM, and people were going to the ATM and they were entering all their information, and that information was being captured by the malware. And when someone came up and put in a MasterCard for the malware, it would write all that information back onto that card. Okay, so what if we had a way to detect the presence of that malware? We're not expecting, like our own machines, we're constantly getting updates of software. There's software updates coming out all the times of applications, operating systems updates. Constantly, our machines are changing. But for an ATM, we're not expecting there to be daily updates to the software. So we're not expecting change. So what if we can detect the change, and then shut down access to that ATM? And not allow the ATM to actually communicate with the back-end servers at that point, and detect that there is an issue and send someone out to service it and shut it down. And that would limit, limit the damage that that malware could do in that particular environment. So the research question is, how do I establish trust of a device that may be reconfigured to provide a different set of functions, intentionally, unintentionally, or maliciously? And how can we establish, evaluate, and maintain platform integrity? And that, with this line of research, basically that's what we're trying to do, is maintain platform integrity, and that the platform performs as specified or as expected as per the certified software stack that, is loaded on it. So basically our notion of trust, we use the classical BIBA integrity model notion of trust, and basically we trust the system, if all of the files on the system, including the binaries, are what we are expecting. So binaries and configuration files are the files that we expected them to be. And the system has to basically be in an identical state. And so, like I said before, the notion of what is trusted is externally defined and not defined by a framework. So you tell me what is trusted for you, and then we can actually plug that into our framework and evaluate your systems based on what you've told me is trusted. Okay. So our proposal is to use trusted computing platforms to enhance the security solution and evaluate platform integrity. So I'll give you a bit of a background on trusted computing and what it is. So it's basically a technology that allows a platform to give unforgeable guarantees about its configuration state. And the way that it actually does that is that within this trusted platform module, a TPM, you have a separate execution environment and storage. So cryptographic keys are actually stored within the TPM environment. And so I can create additional keys that may be stored on the host, but those keys are encrypted using the TPM, and they're never used in unencrypted form outside of the TPM. So let's say, for an example, I'm running a particular software stack, and I encrypt some data, that I want to be protected. And basically, you cannot unencrypt that data unless you're running the same software stack. When I want to decrypt that data, what will happen is that key that I have encrypted on the host is passed to the TPM, and the TPM then uses that key to decrypt the data, and that data is then passed back. So the data, where there is a specific vulnerability with the data itself being exposed, if you have like a malicious DMA control, a direct memory access. So if there's something, if your DMA is malicious, then they could copy the unencrypted data and that type of thing. But with regards to protection of the keys, we're protecting the keys because they're not used outside of the TPM. So basically, a trusted computing platform is a platform that has a trusted component in the form of built-in hardware. And the trusted platform module today, in current systems, the TPM is, about 50% of the laptops today have TPMs. And I expect there to be 100% in a few years. This laptop that I have has a TPM. It's a Dell laptop. It came with a TPM. A lot of the home computing systems actually were being shipped with TPMs. The ones that are used for graphics and gaming and those types of things. And I think that the intention was to detect when people were actually using or downloading games without, having paid for the games and those types of things. But there was never any applications that actually made use of the TPM. Those TPMs that were being shipped in those home computers were never activated, never used at all. And so, but all the machines were being used at one time, maybe a year or two ago. Most home computers were being shipped with TPMs, I guess, with the intention that applications would be developed in the future to actually try to monitor, you know, or limit what you could do with those, whatever graphic applications you were using. But you didn't really see any movement in that direction because it's a challenging problem. You know, how do you, you know, harden a home machine that's changing all the time? It's very hard to do that.
Raquel, I'm sorry to interrupt. Are you using slides there as well?
Yes, you can't see them?
We're not seeing the slides. I couldn't tell from the edge of the screen because we don't see anything, so I didn't want to interrupt.
Okay, let's check that out.
Sorry about that.
No problem.
He has a remote control for their Polycom. He can zoom out.
Much better. Thank you.
Okay. So the trusted computing hardware that we're using in this work, and I talk about in the class, is the Trusted Platform Module, or a TPM. Basically, it has a CPU, and the CPU has functions SHA-1 hash, key generation, and RSA encryption. It has storage, and the platform configuration registers basically 20 bytes long, which is the size of SHA-1 hash, and is used to store measurement records. And what these measurement records are basically hashes of whatever files you ask the TPM to measure. So basically the way the TPM works is that it relies on what is called a core root of trust for measurement. It relies on the BIOS, your basic input-output system. So that actually becomes the BIOS is the initiator of the measurement process. So you must have a trusted BIOS in order for, you know, the whole measurement process to work. The BIOS actually initiates the measurement, measures itself, and basically sends, you know, its own file to be measured, and then the BIOS then loads the OS, and the grub loaders OS and everything else, and that becomes the measurement change to measure whatever is actually being loaded into memory. And those measurements are stored in the platform configuration register. And so what they do is create a hash chain. Every time you measure something, you're extending a particular register with this measurement. And once a remote entity says, prove to me what you're running, basically the TPM will have to send what is called a quote to that remote entity, you know, that is signed using a protected key within the TPM. So if you want to try to fake, you know, the remote system, you need to actually have the key, that's the private key that's stored within the TPM in order to do that. So the TPM, you have a secure report environment that is booted. You securely store data. You identify the user and the system, and the TPM is very inexpensive. Probably a couple of bucks now to actually produce the TPM. And when it talks about identifying the system, that's based on the identification or attestation keys that are created by the TPM to identify the system. So this becomes a problem. Let's say that in order to interact with a remote entity, if I'm just a regular user, I have to tell you what software stack I'm actually running, what OS I'm running, what applications. If the party that I'm reporting this to is a malicious entity, they can determine the vulnerabilities within my system and then possibly try to attack me. So this is why this particular point here, securely identify user in the system, tying a system to a particular software stack could possibly create a vulnerability, especially when you're looking at an individual user situation. Someone can target your system to be attacked and make it into a bot or anything, because it understands what the vulnerabilities are in your system. Because I'm taking a measurement, a hash of every piece of software that's being loaded into memory. So using a TPM to actually, lock down a user system is not necessarily a good idea. Using a TPM to lock down an infrastructure system is a good idea because you have infrastructure that's in one administrative domain. And so you want to control that environment. A user system, you don't want that amount of control. When we think about how could a user possibly use a TPM to benefit the user? If a user wants to know whether its system is in a compromised state or not, that's something I'm interested in, but it's a very challenging problem. If I boot up my system, how do I know that I can trust it? That there hasn't been some piece of software that has been added that may compromise the state of my system. And so that's a very challenging problem on a lot of levels because the user needs to understand what it feels is trusted and not trusted. And a regular user, this is something very difficult to even begin to think about. So regular users may never be interested in using a TPM on that level. They may just want to rely on antivirus software to say, there is no virus that we can detect that we know of. But just because antivirus software can't detect a virus doesn't mean that you don't have some malicious software running on your machine. That's where integrity measurements can help you as opposed to using antivirus software. So trusted boots and roots of trust. Basically, your trust has to be based in something. Okay, so we talked about social trust and behavioral trust. So basically, you have two types of roots of trust. You have the root of trust of measurement, and you have the root of trust of reporting. Your root of trust for measurement is basically your BIOS, and I talked about that, and it basically kickstarts that whole measurement process, and it's the first software that needs to be booted. Your root of trust of reporting basically is the TPM, because it's the one that's going to be asked to give a signed quote of whatever is running on your system. So the root of trust for reporting is implemented as a TPM, and you have measurements or hashes of specific executables, and it could be configuration files or whatever, because our notion of trust is every file that's on your system, whether it's a binary file or a configuration file. And it assigns measurements to ensure integrity and reports them to interested parties. So basically, you can think of this as being a distributed computing environment where you have nodes that need to communicate in order to answer a question or do some type of computation or some type of transaction. In the ATM case, you have an ATM machine and you have the back-end server that it needs to communicate with. And if the front-end ATM is compromised, you really don't want it talking to the back-end server, but you want the back-end server to be able to detect that. Or vice versa. If the back-end server is compromised, you want some way of the ATM to detect that there has been a compromise. So you can have a dual integrity evaluation. So we talked about this, the trusted boot example. This is an example of the measurement chain. So you have your BIOS as the core root of trust for measurement. It must be a trusted software module. And there has been some discussion about actually including the BIOS on the TPM. So you have the BIOS itself in a protected environment, but there hasn't been any development in that area. So you have trust based on social trust of the vendor. The BIOS issues a request to the TPM to measure itself. After measuring itself, it measures the master boot record and on and on and on until you get to the OS that then measures, any applications that are loaded. So your OS also needs to be changed in order to include the hooks into it so it will talk to the TPM and actually to measure it. So the BIOS, if you have this certified, if the BIOS knows what OS should be loaded, you could have something where I have this expected boot process and I know what I expect to be loaded. If the BIOS detects that the OS is not the OS that it expects to be loading, it can stop the boot process right there and just lock the system down. And that is called like the trusted secure booting process. Let's see. So with trusted computing platforms provide three basic functions. One is secrecy, protecting the stored data. And so you may store encrypted code in non-protected space while storing the keys in protected space. So we have this notion of secrecy that I've kind of alluded to. Authenticity, proof that the code or data is trustworthy, and trustworthy based on this is the certified code. It proves itself via the use of keys that are sheltered. So this is the expected certified code, and this is what I expect to be there. So there's that level of authenticity, and I'm going to kind of run through this so I can get to the other stuff. Authenticity of data. After proving that the code hasn't been tampered with, we can attest to any data stored on the system. So if we've sealed the data, you can actually, protect that data and lock it to a particular software stack. Guarding of data code. Local user can access code or data if the trusted computing platform says that is permissible. Okay. The thing is, I think the TPM is an interesting tool to use in order to enhance security, but there are some challenges to using the TPM, and I think this has really stalled research. And research using the TPM in the U.S. has lagged behind other countries, and one of the reasons I alluded to earlier is because people were concerned that the TPM will be used to lock down user machines. So there wasn't a lot of research, let's say 5 years ago, on using the TPM because there was this big concern about it being used to lock down user machines and not allowing users to have the freedom of use of their own machine. There is a steep learning curve with regards to the drivers, the tools, and they exist, but they're not ready to use in a platform. So this particular work that we did, one motivation for doing the work was to bring all those tools together so we could at least have a baseline platform for actually doing trusted computing based work so that someone could come in, plug in the infrastructure, and not have to worry about, do I have all the drivers? Am I running the correct OS? Do I have all the patches and those types of things? It is not a very user-friendly kind of thing to use initially. And so what we did was put this all together in a trusted image so that you don't have to worry about that, in addition with some additional services that we did. And then there's the code diversity problem. And that's the problem that I talk about with our own personal machines, because there are so many different drivers out there for every adapter that we have. We are being bombarded with constant updates. How do you address this and try to lock a system down to what is a trusted certified state? Is a challenging problem. And that's why in this particular iteration of the work, we're actually limiting the types of systems that we're looking at, and these are the infrastructure-based systems. So when we look at the code diversity problem, Windows installation loads like 200 or more drivers from a known set of 4 million. So this is an issue. So if you have 4 million possible drivers, how do you define what is acceptable and trusted within this set? And there are like 4,000 new drivers are reported daily. The amount of operating system state is large, and Windows performs about 20,000 to 50,000 registry reads during the booting process. So if you're trying to do this, within a Windows environment, this becomes a very challenging issue. And this is really the code diversity problem. So some research has been done to actually try to address this problem. Instead of looking at specific executables, they look at the properties that those executables provide. So they're trying to move towards a property-based attestation. So if I have this particular property, for this piece of, if this code provides me this property, then, it meets the, the certification. But not a lot of work has been done with determining how to map these executables into specific properties. And I think that's more of an application domain particular problem. So, but that's the code diversity problem. So with our plug and play static trust, our goal is to enable remote parties to verify integrity of embedded communication systems, thereby limiting the effects of malware in a compromised system. So our system provides remote attestation. But basically, I will prove to a remote party that I'm running a specific code set. Identity verification. Basically, the remote party knows my public key, and only I know the private key that's stored and protected by the TPM itself. So that's how we're doing identity verification. We're establishing a secure communication channel between our peer applications. So basically, we have two nodes that need to communicate, whether it's an ATM machine or you're working in a distributed computing environment, like a grid environment, where the two nodes need to work together for a computation. And we want to evaluate the integrity of the systems. So what we do is that first, the two systems will send each other a quote of what they're running, and only if it's what it's expected to be will they open up a port in the firewall to establish a secure communications channel. And basically what we're using there is that we're using SSL with keys that are embedded within the TPM and protected by the TPM itself. So that's how we're actually doing the secure communication. So with some of the with some of the threats out there. So even if someone, steals a key, they still can't impersonate an entity because they need to be running the software, they need to be running the software stack. So, or if they steal the image, they can't impersonate the TPM because they need the identity, the private identity. So that's how we get around some of those things. So with, basically, our certified trusted state to trusted system means to trust all the files. And for a system to be trusted, it must be identical in every way to the baseline predefined trusted system. Okay. So our approach is that we use the TPM as our hardware notion of trust. We give, which gives us identity verification and remote attestation. We integrate these tools to make it easier to actually use the TPM. Okay, because part of the issue is that I have these TPM tools that will talk to the TPM, but they're not all integrated. And so we use TPM tools. We have OpenPTS and Trousers and IMA, which is our integrity measurement architecture that has been built into Linux. It was actually developed by IBM. And this allows us to enable TPM communication. Okay, and we also use those communication tools in order to develop our firewall service and our attestation application. We use live CD technologies to create a read-only file system image of the certified distribution. So we're creating this, and I'll tell you about later. I'll give you the reason for creating this read-only file system image. But what we also do is create a compressed ISO of the image itself, because what we found, we were thinking, okay, we know we need to measure integrity of the system, and we want it to be a read-only so it's not changeable, because we don't want someone being able to go in and change what is supposed to be certified. So when you boot it up, it's what it's expected to be. But we also learned that we needed to do a compressed image and do a measurement of the large image itself and not the actual individual files. And I'll show you some measurement results that will motivate why we went that particular route. So these are our plug-and-play trust services. We have an application, the quote daemon, that responds to remote attestation requests with a signed quote of the TPM. We have a trust verifier that verifies that particular response. And we're actually, we have random nonces in this attestation request. So if someone tries to replay a request, it's not going to be accepted because we're using the nonce. We have a firewall exception service that basically says, this is the gatekeeper. You cannot communicate with me until you prove that you're in a particular trusted state. And we're using secure communications, using SSL, using TPM protected keys. So those keys are protected using the TPM. They are stored on the host, but they're encrypted using the keys that are stored within the TPM itself. So that allows us, so we're embedding, that trust within the TPM. We're using that secure execution environment. So if the host is compromised, what someone can do is steal the encrypted keys, but they cannot decrypt the keys. So they can't decrypt them because the storage root key of the TPM is used to protect them, and they would then have to go into the machine and compromise the TPM hardware in order to try to gain access to the keys themselves. So this is, our trusted image. We start out with our compressed ISO, and basically those lines actually show you the process of what is actually being loaded into the system. Here we have our sealed data, and basically it defines our network. It gives us the IPs of the nodes that we're going to communicate with. We have our private keys that can be stored optionally, but all of this is encrypted and tied to this compressed ISO. So basically, if someone boots something else within the system, we won't be able to decrypt this data here. So once anything else is loaded in the system, you don't have access to that particular data. So the TPM will not decrypt if what it has measured says that it is not what it expects to be, because we're storing that measurement. Yes.
What if you have a node go down? Does that prevent decryption?
If a node goes down, and does the node come back up?
No, what if it just...
If the node goes down, then the node is not operative, and then so you can't decrypt this data. This data is stored in an encrypted state. So anytime you want to access that data, the TPM, when you make the request to decrypt this, the TPM says, "Oh, what is your current state?" Because every time you load something, it measures what is being loaded into memory, and if that state changes, then you can't decrypt the data. But if your system goes down, that data is still protected because you've sealed it against whatever's loaded into memory. If your system's down, it's not on. Okay. And so we're using this compressed ISO image where we're actually, instead of measuring each binary and each configuration file individually, we're actually measuring the compressed image because it is much quicker to do that. Okay, I've actually talked about that. And so let's talk about how we got to using this compressed image instead of individual files. We actually implemented this using a Dell Latitude, and the Dell uses a TPM version, a Broadcom version of TPM 1.2, and what that has is the TPM is connected via the PCI Express bus, which is much faster than the low pin count bus of some of the other TPMs. And so you have 250 megabytes per second of data versus 2.56 megabytes on the low pin count. So we had a faster bus, which was interesting when we started doing the measurements, basically sending the files over to be measured, because we're not getting that type of throughput. What is actually, why is this? What was happening is that, the requests were being buffered until blocks of data were actually being sent. So all of these measurements are in seconds, and these are the file sizes of data. And what you see, and when we're looking at our file system, we're looking at systems that are about a gigabyte of data. And so it takes 27,127 seconds to measure a file system that has 1 kilobyte size files, for a gigabyte of data. But when we look at a system that just has 1 gigabyte of data, basically what we're getting is about 10 seconds. So that basically motivated us to say, hey, we actually need to measure larger files and not try to do this individually, because it's going to take us, forever to do this. And so what we also did was we also saw that if we pipeline the measurements, we could actually get a better speed up. So what we can, by pipelining these measurements, we get we can get up to 200 megabytes per second, as opposed to getting to 100 megabytes for a gigabyte of data. Okay, so basically that kind of motivated why we actually chose that approach to have this compressed ISO instead of measuring individual files. So this is basically kind of like an outline of how we're actually doing this. So basically you have a plug-and-play embedded service provider, and then you have a user. So the user will request basically for an embedded service on a particular port, and then you have the provider to say, okay, tell me what state you're in, because if you can't prove to me that you're in a particular state, then I'm not going to allow you to communicate with me. And so at that point, the quote daemon will talk to the TPM and ask the TPM to give a particular quote, and the quote is then verified. And if that goes through this validation process with the trust verifier, and you have the validation of the result. If they can validate that particular quote, basically what you get is access confirmed or access denied message going back to the user. And if you get the access confirmed, you have the trusted communication is established. Are there any particular?
Yeah, I have a question. So basically, the user just sends some request to the end, and the provider will do ask the TPM to do the verification. Is that correct?
The provider will ask the TPM. No, the actual TPM is not doing the verification. What happens on this particular side is that the provider has the public key of the user. So it doesn't, that particular service, that validation doesn't necessarily have to be done by the TPM, because that's just the verification of the signature. So the provider in a cache, that's as part of that encrypted data that it has, is the hash chain for the user. Okay, and he also has the public key of the user. And so you can do that in software because you're not compromising anything at that point. So it doesn't have to be done by the TPM. You could ask the TPM to do those services, those verification services for you, but you're not making anything vulnerable by doing that outside of the software.
I'm concerned about the performance here because that doing all even in the gigabyte side of file, it takes 9 seconds or something to do the verification. So I'm thinking about if there is a possibility of kind of like a denial of service, because some kind of user just send a request to the provider, and if the provider do something, so maybe because it takes.
Okay, I understand what you're saying, but the 9 seconds is for the boot and measurement process. So that's when a system is actually booting up. It's not for the exchange and the quote verification process. So those are two different processes. It takes when a request is like when the provider actually asks for a particular quote from the user, that whole process, that exchange takes about 1 second.
Okay.
So it's not like the 9 seconds. The 9 seconds is I'm booting up my machine and I'm actually measuring everything and I'm loading everything. So it takes about 9 seconds for us to boot up and measure.
And then it's cached. And when the request is sent there, they just send back the cached chain of verification.
Yeah. So that after that, when someone asks you for a quote, you don't do a measurement all over again. You take what's currently been loaded and measured. You don't do the whole boot process over again. So yeah.
Okay, thank you.
Okay, there are 2 questions here. I'll take your question first.
I have a question about the SSL transactions between local and remote. Do you use self-signed X509 certs, or is there a trusted third-party certificate authority?
See, that's that becomes an issue with regards to the infrastructure itself. So we don't because we are assuming that you're in one administrative domain, and so that administrative domain is responsible for issuing those certificates. So if you had a trusted third party that you're using within your administrative domain, that's one thing. So these keys are actually created by the TPM, and then you would need an entity within your administrative domain that then certifies that this is the TPM's key. So the storage root key is actually on a TPM, is signed by the vendor and everything. So you have the signature chain for the TPM storage root key. So the TPM signs that, and then you can have a entity that's responsible for that.
I think there's some potential vulnerabilities there.
Okay.
Just because of the existing attacks on X509 and
Yeah.
SSL.
So yeah, that could possibly be an issue. Yeah. Camilo.
I have two questions.
Mm-hmm.
One, so from this image, it seems like the service provider knows all the private keys necessarily from start.
The service provider knows the public keys.
The public keys.
Yeah, from the start. Yeah. So
And the private keys are part of the hardware per se that we're.
yeah.
So if the hardware crashes, that key is just a goner.
Yeah. If the hardware crashes, that key is over, and you're going to have to basically recertify this particular machine.
Second question.
Mhm.
Okay. The attestation, as you show, basically it attests that up to the moment where the machine, after the moment where you attest it, that machine hasn't changed. But if someone attacks you after you build your cache, and then just replace that data, then
Yeah, there's an issue with the time of use versus time of check problem, and this is a problem that exists, with regards to TPM. So let's say, I think what the question you're saying is that there's a vulnerability. Let's say that the user makes a request for a service from the provider. The provider says, okay, I want you to send me a quote. He sends the quote back, but somewhere in between here and here, there's a change on the system. And so that allows for the system to go through the authorized message, and establish a trusted communication. Now, in order to try to get around that, what you would have to do, or to address that particular issue, the provider needs to periodically challenge the user. So it can determine that the user's state has actually changed. Now, let's say the user states change, and before the provider can actually challenge it again, the malicious software goes away and it's rebooted and those types of things. So if it reboots, it has to then, go back through the challenge process. So there may be a window of opportunity where some malicious entity comes in and you can't detect its presence. But in the case where the malicious entity comes in, even after a quote has been verified, what you need for the provider to do is have some frequency of re-challenging the user.
But isn't it also possible for me to, after, let's say, after the trusted system is built, and it's ready to go, so some sort of compromise, and then just fake the transaction with basically be a man-in-the-middle attack. So when the TPM is trying to read the cache data, it reads the updated value image. But when actually it's trying to, one thing is, after we compromise, we present one thing to the TPM and one thing to the rest of the system.
Okay, so where are you saying that is the compromise on the provider, on the user in your scenario?
On the user.
Okay, so you're saying that
You start your system. It's it's attested that is on a known state. Then it's very trustworthy. Someone attacks you. Compromises your system. Now, this compromise system, how do you prevent this compromise system from presenting it itself? Kind of two phases. One phase to the TPM, and one it behaves one way to the TPM, and behaves one way to the rest.
well, I guess one of the things is
Since you're only checking this cache,
okay.
the execution state could be completely different.
I'm checking the cache on the provider. The provider is checking its cache. The measurement is actually coming from what is stored in the TPM of what is loaded. So there are a couple of different types of attacks, right? Let's say, for an example, some malicious entity comes in and it loads, through regular application loading process, a piece of malicious software. The TPM itself will measure that, and it will change its measurement. Okay.
So it's the TPM is checking.
The TPM, everything.
The runtime images. You said it was checking something is stored on memory.
No, the thing is, what the provider is doing is taking that certified state that it has of the user and verifying it against what the user sends to it. But the TPM is always measuring what is being loaded in memory. Whatever is being loaded into memory, the TPM measures it. So now the question becomes, how can I get around the TPM actually measuring, some change? The way you can actually get around that is that if the malicious party exploits a buffer overflow attack and introduces something into memory and it's not loaded through the regular boot process. Now that kind of attack, we can't deal with that. But if it's a regular loading through
the boot step.
Yeah, through the boot step, through the operating system loading something, I can detect that. But if you're launching some type of buffer overflow attack, you can get in there. No TPM measurement was, issued, and stuff, and you've loaded something into memory. That's why I said this is not a complete solution. Nothing is totally secure. But this actually addresses a class of problems that we still have issues with, because we don't have signatures for every type of malicious software that is out there. And for these types of systems where we have limited state, where we don't expect there to be much change, we can actually measure the integrity of those systems. But if there are vulnerabilities like buffer overflow attacks, even within our trusted image, although this image is certified, it doesn't necessarily mean trustworthy.
Yes.
Okay. Are there any? Yes.
I have a question on this point. So, from this point, I think because you just said because it doesn't deal with buffer overflow type of things. So, in other sense, if there is a hard patch, so you don't have to reboot the system to do the upgrade to patch those vulnerabilities. There's kind of updates like this. So, but by using the TPM and your system, you have to reboot and get another quote for your system to, in that kind of scenario. So basically, you have to reboot every time you do the upgrade, right?
No, you don't have to. When you say upgrade, what do you mean? What is being upgraded?
For example, a new patch of some software, which fixes the buffer overflow problem, right?
Yeah.
A lot of systems like Linux, you don't have to reboot. You just have to upgrade the software with that vulnerability. But in this case, by using the TPM, you have to reboot and get a new quote every time you do this upgrade, right?
Well, if your upgrade doesn't require a reboot, you don't have to reboot. If that upgraded software is loaded into memory, the TPM will measure it. If it's loaded through, like the operating system is loading it or whatever, it will be measured. So it's not like you're requiring a boot every time you load a new piece of software into memory.
So how did every party knows this upgrade is authentic rather than malicious?
And see, that goes back to what is considered to be your trusted certified state. And when you look at this, I'm assuming that this is going to be, this type of model is going to be used in an infrastructure that has one administrative domain. And so the administrators decide what is certified and what is trusted. It's not like you can just load something new and, oh, that's trusted. No. You have this pre-certified state that's defined a priori. So if there's a new patch, the administrator has to say, here is the new patch. And here's the new certified state for user A. So, you just can't go in and load something and assume that's going to be trusted by your provider. The provider is one that's going to be deciding, the administrator of the provider decide what is trusted, a trusted certified state, and what is not trusted.
Okay, I got it. Thanks.
All right.
I think there also might be a potential for a vulnerability because of the use of SHA-1.
Yeah.
And I'm wondering if maybe we need a new generation of TPM.
There probably will be a new generation of TPM that's using something other than SHA-1 as the hash. Yeah. So, there are definitely SHA-1 vulnerabilities with short keys. Are there any other questions? Okay, I think I got about 5 minutes, and that gives me time to talk about, where am I going from here with this work. So basically what we've done is develop a platform for trusted computing research. So this is really at the beginning of looking at these infrastructure-based systems, providing this platform so then we can begin to build upon that and building trustworthy infrastructure. That's where we are. I think that there are a lot of applications for this, especially when we look at our electrical grid, when we look at cloud computing. If I am a cloud computing vendor and I'm trying to sell my services to someone, and if I'm a cloud computing client, and I want to ensure that basically you're running trustworthy software, or that my systems are not being compromised, how do you then begin to negotiate that trust between the two entities? I think right now we don't have any solutions, for that. And for, when we look at some specific cloud computing environments, what they're using, what they're booting into, like the virtual machines, are like specific images. They booted an image and not just, individual software and things like that. So it's a little bit of a controlled environment. So that may be a particular application environment. We're looking at how to reduce the size of the file system image to work with systems that have smaller and limited storage. And we wanted to find mechanisms and tools for evaluating the trustworthiness of a software stack. I had specific ideas of, how does someone know what is trustworthy? So if I'm a client of a cloud computing, vendor, if they tell me, oh, I'm running X, Y, and Z, along with your software that I'm supposed to be running, how do I know that that's trustworthy? So I think we need to develop tools to evaluate the trust of, those particular software stacks, because they can tell me anything and say, hey, this is what I'm running. Your software is running in a trusted environment, or your data is being secured in a trustworthy environment, and me as the client, I have no way of evaluating, what they've told me, because certified doesn't mean trustworthy. And if you are a provider of services, for me, then I need a way of evaluating what is trustworthy. So that's the direction that this particular work is going into, and I think there's some interesting questions that haven't been addressed with this work. So if there are no more questions, thank you for your time.
I think a really good candidate for the system would be electronic voting machines.
Yeah, and I have been doing some work with electronic voting machines and actually using a cryptographic coprocessor to protect all the data that was stored, and I got those from IBM, and this is a very interesting device. Basically, if you try to tamper with it, it's an adapter that you plug into the machine, it just self-destructs. It will overwrite everything, but that protects the data. It doesn't say anything about the software that's being running and what is actually running on the machine. So I see this being used in conjunction with the hardware that's doing the protection of the electronic ballots. So that's some work that I had been looking at also. Okay. Yes.
I'm just curious, that example you gave at the beginning about the ATM, if someone were to try to install something that would read information from magnetic strips, would they actually have to access the machine itself? What kind of network are ATMs usually on? Like, do they go through regular internet service providers?
Well, you know what? I think that some of them may go through regular internet service providers, and there may be some direct, links between some. So maybe banks have T1s to their back-end servers, but some of them are probably going over internet service providers, and what they do is create a VPN in order to create that, trusted environment. So you probably have a level of encryption for that data either way you go, whether you have your own dedicated link or you're going over the internet and you're creating, security that way. But even with that, that level of protecting the data that's being transmitted, it doesn't, look at what's actually running on the machines themselves.
So it wouldn't necessarily have to be an inside job for someone.
It wouldn't have to be an inside job for someone to actually do it. But if it is an inside job, it makes it, harder, to detect. Okay. Well, thank you all for coming this late in the semester. Are there any more